Hi everyone. In today's video, we are going to look at a technical problem that often appears in quantitative interviews. The structure of the video will be the following. In the first part, we will review the theoretical results we need, and in the second part, we will apply them to solve the problem. Let us begin by reading the problem statement. Let W of t be a standard Brownian motion. We define the process x of t as follows. X of t is equal to the integral from 0 to t of w of s ds. We are asked to 1. Determine the distribution of x of t, meaning we want to find how the random variable x of t is distributed. 2. Decide whether the process x of t is a martingale. Let's start with the theoretical background. First, let us recall what a martingale is. We fix a filtered probability space consisting of the sample space omega, a sigma algebra F, a filtration Ft, and a probability measure P. Then we consider a stochastic process Mt. The definition of martingale requires 3 properties. First property, the process must be adapted to the filtration. Intuitively, this means that m of t does not see into the future. Its value at time t can only depend on the information available up to time t and not on information from later times. Second property, integrability. This means that the expectation of the absolute value of mt is finite for every time t. Third property, the fair game condition. For any 2 times s and t with s less than or equal to t, the conditional expectation of m of t given fs is equal to ms. This expresses the idea that the best prediction of the future value mt, given everything we know at time s, is simply the current value ms. Now let us recall the definition of a standard Brownian motion. We always fix a filtered probability space. A stochastic process W of t is called a standard Brownian motion if, first, W of 0 is equal to 0 almost surely. Second, the process W of t has continuous sample paths. Third, for any 2 times in t with 0, less than or equal to s, and s less than t, the increment w of t minus w of s is normally distributed with mean 0 and variance t minus s. And fourth, for any such times s and t, the increment w of t minus w of s is independent of the sigma algebra f of s, meaning that future increments are independent of the past. Let us now look at the fundamental properties of Brownian motion that follow directly from the definition. First, for every time t greater than or equal to 0, w of t is normally distributed with mean 0 and variance t. Second property, the process w of t is a martingale with respect to its natural filtration. Third property, Brownian motion has a specific covariance structure. For any 2 times s and t, the expectation of w of s times w of t is equal to the minimum between s and t. Let us explain the meaning of the integral from 0 to t of w of s ds. Since Brownian sample paths are almost surely continuous, for almost every fixed outcome omega, the mapping that sends s to w of s of omega is continuous on the compact interval from 0 to t. Thus, the stochastic process xt of omega, defined as the integral from 0 to t of ws of omega ds, is simply a standard Riemann integral, and hence also a Lebesgue integral. We now recall an important property of the integral of Brownian motion. A stochastic process g of t is called Gaussian if for every finite collection of times t1 up to tn, the vector consisting of g of t1 through g of tn has a multivariate normal distribution. It is a well-known result that the integrated process x of t, defined as the integral from 0 to t of w of s ds, is a Gaussian process. Now, we want to recall Fubini's theorem. We consider 2 sigma finite measure spaces, A with its sigma algebra and a measure mu, and the same for B with measure nu, and let f from A times B to the real numbers be a measurable function. If f is integrable with respect to the product measure mu tensor nu, then both iterated integrals exist and the order of integration can be exchanged. In formulas, we can write the integral over a of the integral over b of fd nu mu is equal to the integral over b of the integral over a of fd mu d nu. We now apply Fubini's theorem to stochastic processes. If we have a function f depending on s and omega, and the absolute value of f is integrable with respect to the product measure Lebesgue times the probability measure p, then we can exchange the order of integration. This gives the identity, the integral from 0 to t of the integral over capital omega of f dp ds is equal to the integral over capital omega of the integral from 0 to t of f ds dp. If we write y of s of omega equal to f depending on s and omega, then this becomes the familiar identity. The expectation of the integral from 0 to t of ys ds is equal to the integral from 0 to t of the expectation of ys ds. In other words, under the integrability condition, we can exchange expectation and time integration. Now it is time to see how the theoretical results we have just reviewed help us solve the original interview problem. Recall that we have defined the process xt as the integral from 0 to t of w of s ds. From the theoretical background, we know that xt is a Gaussian process. This means that for each fixed time t, the random variable x of t is Gaussian. Therefore, to determine the distribution of xt, we only need to compute two quantities: the expectation of xt, and second, the variance of xt. Let us start by computing the expectation of xt. By definition, the expectation of xt is the expectation of the integral from 0 to t of WSDS. Now we use Fubini's theorem. Under the integrability assumptions that we discussed before, Fubini allows us to exchange the order of expectation and integration. Therefore, we obtain the integral from 0 to t of the expectation of w of SDS. Now we remember that for each fixed time s, the random variable ws is normally distributed with mean 0 and variance s. Since the mean is 0, the expectation of w of s is equal to 0. So, it leads to the integral from 0 to t of 0 ds, which is equal to 0. We conclude that the expectation of xt is equal to 0. Let us now compute the variance of xt. Since x of t is a centered Gaussian random variable, its variance is equal to the expectation of xt squared. This, by definition, is the expectation of the square of the integral from 0 to t of WSDS, that we can rewrite as the integral from 0 to t of WSDS, times the integral from 0 to t of WU du. At this point, we apply Fubini's theorem, which allows us to move the expectation inside the double integral. Now we need to compute the expectation of Ws times Wu, but we know the covariance structure of Brownian motion. For any 2 times s and u, the expectation of Ws times Wu is equal to the minimum between s and u. We now compute explicitly this double integral. First, we split the square into 2 triangular regions, because on one region s is less than u, and on the other region u is less than s. On the region where s is less than u, the integrand is s, while where u is less than s, the integrand is u. Now, it is trivial to compute each inner integral, and then solving outer integral. Therefore, the variance of x of t is equal to t cubed divided by 3. We have now determined that xt is a Gaussian random variable with mean 0 and variance t cubed divided by 3. Let us now check whether the process xt is a martingale. We start by rewriting xt in a convenient way. We split the integral from 0 to t into 2 parts, from 0 to s and from s to t. This gives that xt is equal to x of s plus the integral from s to t of WU du. To check the Martingale property, we must compute the conditional expectation of xt given fs. Using the linearity of the conditional expectation and the fact that xs if fs measurable, we have that the conditional expectation of xt given f of s is equal to xs plus the conditional expectation of the integral from s to t of WU du given f of s. Now we apply Fubini's theorem in its conditional form, which allows us to exchange the conditional expectation in the integral. Next, we use the property of Brownian motion. For u greater than s, the conditional expectation of WU given fs is equal to ws. Since ws is constant in the last time integral, this simply becomes t minus s times ws. Putting everything together, the conditional expectation of xt given fs is equal to xs plus t minus s times ws. This additional term is not equal to 0 with positive probability whenever s is greater than 0. This shows that the fair game property does not hold, so the process xt is not a martingale. Thank you all for watching this video. I hope you enjoyed the walkthrough and found the explanations helpful. If you liked the content, please make sure to leave a like and subscribe to the channel. It really helps the project grow. Also, feel free to let me know in the comments any suggestions you may have, topics you would like to see in future videos, or specific quantitative problems you want me to cover. Thanks again for your support, and I will see you in the next video.